right? So in this case study, I explained you on how to do normalization for one energy variable, right? For one energy variable. If you have more energy variables, you can use the same method, right? You can use the same method, but the input for X can be several energy variables, right? Input for X can be several energy variables, right? After getting a regression summary, right? You need to eliminate, you need to eliminate the energy variables that the p-value is higher than 0.1, right? Then you need to run the regression without that variables again. Then only you can get a good, strong regression model, right? Since the p-value is much lesser than 0.1, and also the R squared is almost 9.3, 0.93. This model is this model is this model is a accurate model, much accurate model. In here, the R squared value is mentioned 0.91 because uh, confident level we took as 95%. But when we did the regression, we select the confident level as 90%. So that's why the R squared value is much higher, right? So by conducting this kind of analysis only, you can identify the proper energy performance indicators, right? So I know most of the companies identified simply the ratio as the energy performance indicators, right? No matter what you are doing, you identify the ratio as your energy performance indicators, right? Right. If you have any doubt, when you go for work in the next day, you can check. You can check. So you will be able to verify what I was saying, right? Most of the companies use ratio as the energy performance indicators, but it's not always accurate. So now you know how accurately define an energy performance indicator. So you need to gather energy variables, right? Once you gather energy variables, you need to identify the quantifiable energy variables. Once you identify the quantifiable energy variables, then you need to gather data for the baseline period, right? After gathering data for baseline period, then you need to run a linear, nonlinear regression, right? Linear, nonlinear regression to identify, to determine the energy performance indicator, right? Once you do that regression, right? Once you do that regression, then you can identify whether you can go with a simple ratio or you need to have a single variable or multivariable regression model as the energy performance indicator, right? If in case you get a single or multivariable regression model as your energy performance indicator, right? Then the value for the value you take from the theoretical calculation, which means from your defined energy model, would be the baseline, right? Which means you compare your current actual energy performance against the theoretical value, right? Comparing your current energy performance against the theoretical value, then you can calculate the saving month-wise, right? And at the end, you can calculate the cumulative sum of saving. That's how you need to present your energy performance to the management. So there is a risk. There is a risk. If you have if you have failed to identify the proper energy performance indicators, then you definitely not be able to report your energy performance to the management, right? If your energy performance indicator is wrong, then the effort you have put on the projects, the money you have invested for the projects will not reflect from your energy performance, right? Will not reflect from your energy performance. So if you need to reflect the money and the effort you have put on the projects, when you are presenting the energy performance to the management, the most important thing you need to do is to identify the proper energy performance indicators. That's the key summary of these 2 hours, right? To identify the proper energy performance indicators, you need to identify the variables, then you need to identify the quantifiable variables, then you need to get the data, right? If you do not have data as of now, so your first step should be you have to plan to gather energy data, which means you do not have submeters, you need to logically implement submeters. So if you do not have meters, flow meters to gather energy data for steam consumption, then you need to implement steam flow meters first. After implementing those meters, you need to first gather energy data for at least consecutive 12 months, right? Another practical problem you might face when gather when gathering energy data is the accuracy of the meters, right? So before you gather data, you need to calibrate all the monitoring and measuring equipment you use to gather energy data, right? We know in Sri Lanka there aren't a facility to calibrate power analyzers. So at least you need to do a verification, right? Do a verification. After doing a verification, you can identify whether that particular meter can be used to gather energy data or not, right? Because if the accuracy of the data is low, right? If the accuracy of data is low, then you will not be able to get strong regression models. If you do not get strong regression models, then you will not be able to highlight your effort and money you have spent on the energy performance, energy improvement projects. Right. I think during these 2 hours, I tried to explain the concept of energy baseline and energy performance indicators, as well as how to do an energy review using a practical set of data, right? So you can refer to the standard of ISO 50001, and also there is a separate standard for energy baseline and energy performance indicator calculation. There is separate ISO standard, ISO 50006. So you can buy that particular standard and you can read and enhance your knowledge, right? So when you are implementing ISO 50001 energy management system within your organization, now I believe you have practical insight, right? You have practical insight of how to do that. And during the next session, Pushpika will explain the energy saving strategies, right? The energy saving strategies. So we identified the projects now. So how we are going to identify the projects? We identify the projects either based on our experience or either as an outcome of the energy audit, right? As outcome of energy audit. So either by experience or as an outcome of the energy audit, you can identify the projects. Right. Once you identify the projects, then Pushpika will explain you the energy saving strategies, and you will be able to know what are the areas you need to focus and how you prioritize the projects. So those things will be explained by Pushpika, I think after lunch. So if you have any questions, please drop a message. If you are if you are not willing to ask, so you can simply drop a message, right? So good luck for the next session. And I think Shehan, you can take over. And thank you very much for all the participations for participating today.
Thank you, Mr. Hashan, for that practical and insightful session. So now we'll go for a lunch break. We'll resume the program at around 2 p.m. for our final session. So yeah, please make sure to join us on time as the next session will focus on practical strategies to reduce energy consumption and improving operational efficiency. So enjoy your lunch and we'll see you shortly. Welcome back, everyone, and I hope you had a refreshing lunch break. Now we will proceed with the final session of the Energy Excellence Masterclass organized by Halcyon. Let me introduce our final speaker, Mr. Pushpika Jayakanta, a sustainability expert consultant. In the final session, he will cover the identification of high energy consumption areas, operational efficiency improvements, behavioral energy saving programs, and then he'll link the energy management system with ESG and sustainability goals. So without taking further of the time, over to you, Mr. Pushpika.
Right. Thank you very much, Shihan. Hope you all can see my screen. Shihan?
Your screen is visible, sir.
Okay. So good afternoon, everyone. So welcome to the session 3. Here actually we mainly focus on energy cost reduction strategies for industries. So in previous session, I think you had discussed ISO 50001 energy management system framework and energy review process and energy performance indicators with Ms. Rasita and Mr. Ashan both. So now we'll move from theory to practical energy performance improvement strategies. So this session focus on identifying where energy is consumed and how organization can systematically reduce energy costs through operational improvement and technological updates. So the objective of this session is to provide practical understanding of energy cost reduction strategies. So by the end of this program, you will be able to identify significant energy users within the industrial operations, understanding how operational inefficiencies increase energy consumption, and implementing low cost and no cost energy saving opportunities, evaluate your energy efficiency projects or investment using financial tools, and understanding the relationship between the energy management and the sustainability. So these concepts are essential for organization implementing the energy management system under ISO 50001. So before we start, I have one question from you all. So are you aware of how much energy costs contribute to your production cost as a percentage? Hope there are industry people also here. So I need your feedback. You can use microphone or the chat. Or if you are all from the university background or undergraduate, so then you can guess. Can you guess how much energy cost contribute to the production cost as a percentage in industries? Any guesses or any answers? Team, are you there? 80%. Yasita Rajapaksa said 80% energy contribution. Okay, good. Anyone else? Yasita, what's your background? From industry or you are from the universities?
I'm undergraduate.
Undergraduate. Okay, good. Anyone else? Anyone? No feedbacks? Okay, around 30%. Okay, I need more feedbacks. I think there are so many people here. Yeah, there are 40 people. I don't know whether all these are participants, but there are 40 in this list. So I need more feedbacks. Can you guess? Yasita said 80%. Sindhu, ja, I think I'm right. Sindhuja says around 30%. Anyone else? Is it between 30 to 80 or below 50? You can guess. No feedback? Prabhashi Manushika, 30 to 10 to 30. Okay. Below 50. Dahan says 20%. Okay. 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 Let's move forward. I think 10 to 20%. Okay. We get more feedbacks. Again, another 70%. Okay. Let's move forward. Let's move on. So in many industries, this energy cost typically represent 5 to 20 or 30% of total production cost. And actually this depend on the industry type. For example, food processing or food industries, it can be within 5 to 10%. Textile like industries 10 to 15%. And chemical manufacturing industries, it's around 15 to 20%. Steel and cement like industries, it's around 20 to 40%. So it vary actually, it really depend on the industry. So this is why energy management is extremely important, and this even 10% reduction in this energy consumption can significantly improve the overall profitability of production process. And the most important one is many of these improvement can be achieved without major capital investment. So when evaluating energy consumption in industries, it is important to consider all energy sources. I think you have discussed this with Mr. Rasit and Hashan both. So we have to consider all energy sources, not only the electricity. So it can be electricity, natural gas, fuel, diesel, biomass, or renewable energies. And this energy consumption pattern vary depending on the type of industry and the production process. For example, the industries with high mechanical process often have significant motor energy consumptions. And industries that rely on heating process often have high consumption of furnace, ovens, and boilers. So understanding this pattern is essential for identifying significant energy uses. So this energy consumption profile varies significantly across industries. So in these textile industries, the steam and motors are typically dominant energy users. Food processing industries, thermal process such as baking or drying may dominate. Sometimes the cold chain operations are dominant. And in glass or ceramic industries, furnace often represent the largest energy consumption. And electronic manufacturing kind of industries, significant IC loads due to environmental control requirement. So this variation demonstrates why every organization must conduct its own energy review. So now we'll move to the next session, the identify high energy consumption areas. I think you have some basic understanding about these elements with the previous session engagement. So this energy management begin with identifying significant energy users. Commonly we call this as SCUs, significant energy users. So these SCUs or significant energy users are the system or process that consume large portion of energy or offer opportunities for improvement. So identifying significant energy users allow organization to focus improvement effort where the largest impact can be achieved. So there are several methods we can use for this one. So here we considered utility bill analysis, production intensity, energy intensity analysis, energy audit, submetering, and real-time monitoring system. So utility bill analysis provide the historical consumption data. So you can start with that one. And the production energy intensity analysis related energy consumption to the production output. And the energy audit evaluate the energy performance of equipment and the process. And the submetering measures energy consumption of individual systems. And the energy monitoring system provides real-time data. So these methods provide comprehensive understanding of energy use. So we'll go one by one. Utility, I said that you can start with the utility bill analysis. So this provide valuable insight into energy consumption patterns. They contain information about the total energy consumption, peak demand, the energy cost. So analyzing trends over time can reveal seasonal variations, abnormal consumptions, or operational inefficiencies. So utility bills, you can use this utility bill as your first step for the energy analysis, for the energy review. The second one is energy performance indicators, so ENPIs. I think you have discussed this with Hashan. So these are metrics used to evaluate energy performance. So you can use kilowatt hours per product, tons of product or kilo of product or kilowatt hours per machine hours, fuel consumption per production bed. You can set energy performance indicators according to your organizational requirement. So these energy performance indicators allow organization to measure improvement over time and compare this performance against benchmark. So this is the equation, energy consumption divided by production output. We call it as energy intensity or energy performance indicators. And then the energy audits. This is somewhat technical analysis assessment. So energy audit involves the systematic evaluation of energy use in a facility. So audit assess the performance of equipment such as boilers, compressors, motors, and these AC systems. So the objective is to identify energy conservative measures. So this energy audit can be classified as preliminary audits. We call them as level 1 energy audit. And then the detailed energy audit, level 2 audit, and the investment grade audit, we call them as level 3 energy audit. So this energy audit, by using this energy audit, you can identify the inefficiencies, system or process within your energy management system in your organizations. And then the next one, submetering. So this involves installing meters at the system level. So instead of measuring only total facility consumption, submeters measure energy used for specific equipment or production line. So this improve energy consumption visibility and allow organization to identify inefficient systems. Then the energy monitoring system. So these system provide continuous measurement of energy consumption. So they typically measure electricity consumption, demand, power factor, operating hours, and some advanced system. They provide automated alerts when abnormal consumption pattern are detected. So this energy monitoring is essential for continuous improvement in energy performance. So this is actually the combined task. So these slides illustrate how these different management practices come together to form a continuous improvement cycle for operational efficiency. So you can start with utility bills and energy intensity, and then you can plan energy audits to identify the significant energy users. And then the submetering systems, you can implement submeters for specific processes or the areas or production lines. And then you can go for the advanced system like energy monitoring system. So then with the all of these data, the information, you can systematically update and continuously improve your energy management system. So doing this, when doing this assessment, the energy mapping is one another most important part. So this energy mapping provide visual representation of energy flows within your facility. So energy enters the facility from various sources. So energy sources has different efficiency characteristic and environmental impact. So understanding energy source is very important for evaluating uh, uh, improvement opportunities. And these energy distribution systems then transport energy from the sources to the end use equipment. For example, this electrical distribution system, steam pipeline, compressed air distribution networks, and hot water system. So energy losses often occur in distribution system due to leak, insulation failures, or pressure drops. And then the end users. So end use system include the equipment that directly consume this energy. They also can energy losses due to leakages, uh, heat losses, and inefficient equipment. There also can be some losses. So identifying these losses is a critical step in energy performance improvement. And for that part, actually, mainly energy audit and monitoring system help to detect those losses very effectively. Right. Uh, Now we have one case study here. So I will share this case study with your WhatsApp group. Right. I think you can access that case study in your WhatsApp group. So here, a textile manufacturing facility operate 24 hours per day for 300 days per year, and the plant produce knitted garment and consume significant electricity for boilers, chillers, compressors, and motors. And the management has identified rising energy cost and lack of structured energy performance tracking. So here, uh, they have provided utility bill data for last 6 months and their production record, electricity cost, and the maximum demand. And same time, they have provide the submetering data for the production motors, compressed air systems, chiller system, and lighting and utilities. And provide some technical data here. The compressed air system has the estimated leak of 25%. Chiller system has the potential of 20% energy saving, and the boil efficiency is 75%. So now you have questions, 5 questions. Analyze the trend between production and energy consumption, high inefficiencies and abnormal patterns. What is this? Maximum demand. Yes. There's an issue with that one, Daham. Good point. It should be kV, yeah, not kWA. The unit should be changed. So you have 5 questions. You have to calculate the energy performance indicators for each month and identify best and worst performance, and calculate the performance energy contribute of each system and identify significant energy users. Task 4, estimate potential savings from compressed air leakage and chiller efficiency improvement. Finally, you have to propose the recommendations. Can you do this case study? Team, can you do this? Daham, can you do this? I need feedbacks. I think you can use these reacts here. Can you do this program, this case study? You got this case study clearly? No comments? Yasita? Prabhashi? Any comment, teams? Or else I will not allow you to do this case study within the session. So I will move forward. What do you prefer? Shall you do this? Okay, Daham said, okay. Others? So you are sleeping? Are you all sleeping now? Okay. So I will give you 15. I will give you 15 minutes. So you can do the case study and you can put your answers into the chat or WhatsApp group, anything. I can access the both. In WhatsApp group, I shared one Excel sheet, including all data, so you can use that one. So it is easy for you to do the calculation using the Excel sheet. Anyone get answers for the task one? Okay, once you're done, you can put the answers into the chat or the WhatsApp group. Okay, we got 2 feedbacks. For task 1, the hum says task 1 January, February, April, May. The what is this? The So in task 1, you have to identify the trends between production and energy consumption and identify inefficiencies and abnormal patterns. So I think the hum says there's abnormal pattern January, February, April, May. I don't know. Yeah, abnormal and abnormal energy consumption. Okay, good. Michelle says energy consumption is increasing even when production drops. Yeah. Yeah, good observation there. So we'll go to the task 1 data here. Yes, Michelle, and the harm, it's correct. Here you can see this actually the energy does not reduce when production decrease. So you can take this, you can see in March, April, production decrease, but energy remains high. So this indicate, so this is actually you should go into deep. So this indicate the presence of high base load in this facility. So base load, do you know about the base load and all the thing? I don't know whether you get these terms in previous sessions. So base load is the portion of energy consumption that remain constant regardless of production levels. For example, if there's one production line or 2 production line, definitely you have to run the boiler. So if there's let's say that 2, 3 floors building, in one floor there's only one department work, but if there's a central AC system, then definitely they have to run that AC system. So there's a base load for that particular building. So in this case, actually the base load is high. Base load can be high. This can be due to the possible causes like that utilities running consistently, and sometimes poor shutdown practices. Those are the very common thing in the industries. And then sometimes the switch on the auxiliary systems, the lighting AC or the cooling water systems continuously. So then it can be increase the base loads. So this lack of proportional reduction in energy consumption with decrease in production indicates the significant base load. So here you can take January as one baseline here, because if you calculate the energy performance indicate, it is the most suitable or the minimum energy performance there. So you can say it as a baseline. And then the trend is actually there's no upward or downward trend. The trend you can simply say this is not actually tally with the production data. So this energy does not reduce when production decrease. And these are the key observations there. So this high energy performance value during low production months, evidence in this April. April you can see April, May in both low production but high energy consumption. And this if you go to this demand values, maximum demand values, it actually increasing. So demand increased from 1,250 to 1,400. So this suggests again poor load management and demand controls. So this can be due to simultaneously startup of equipment, no demand side management system, no peak time operational and high load equipment management, and lack of staggered operations. So this increase in demand trend indicate inadequate load management again in practice and result in high peak demand and increased energy cost exposure. So in April, May, and sometimes in June, there's a moderate production, but again, high energy consumption. So this again, this is inefficiency and operational losses due to the poor energy performance. And this actually, you can justify there's no stable energy performance trend here actually. There's no any stable energy performance trends because the energy performance indicators, if you calculate in the task 2, this energy performance indicators also fluctuate significantly. So again, that is due to the lack of control energy management system. Okay, so there's no stable trend here. The production, even if the production decrease, the energy consumption is high. So you can analyze this production by setting this kind of graph production into the energy for this particular months, and then you can decide it. And then the energy performance indicators, I think you have done this one also. Yeah. Michelle, task 2, best January, worst April. Yasita, best January, worst April. Yes, that is correct. So you can see here, you have to divide this energy consumption by the production, and then you can get these values. So January is the best value and best month, and the April is the worst month. So again, this variation indicate these operational inefficiencies and poor energy controls. Okay. Significant energy users. Michelle, your calculation is correct. So then you have to select what are the significant energy users here. So in first slides, we justify that one. The significant energy users are the substantial energy users. So the area there's a potential for the energy improvement. So then you have to select what are the significant energy users here. Okay, Michelle says production motors, compressors, and chillers. It says selected three areas. Why is that? Why, Michelle? Why you?
Highest consumption is coming from those areas.
Yeah, good. Highest consumption. So, okay, let's move with the answers. So you're correct, Michelle. The production motors, it's 40% contribution there, compressed air 21%, chiller system 27%, and lighting and utilities 12%. So you have to get these ratios, you have to first identify the total energy consumption of these four areas, and then you have to divide this particular energy consumption area by the total. So then you can get this 40, 21, 27, and 12% values. And why we have to focus the three parts: production motors, compressed air, chiller system. Michelle is correct, because the 88% of this total energy is represent these three areas. So definitely we have to focus those areas for improvement. Okay. Next one, potential energy saving opportunities. Energy saving, I need the annual value. Huh? So in this case study, there are two hints. There's a estimated leakage 25% for compressed air system and chiller system. There's a expected improvement of 20%. So you can consider that one and calculate the energy saving opportunities here. Team, I need more feedbacks. There's only few people. I feel there's only few people doing these case studies. Daham, Yasita, Michelle, any feedback for this task 4? Do you need more time for this one? Chamara, Divyanjali. Michelle, it's better you convert this into the financial figures. So then the management can take the decisions easily. So energy saving opportunities for the estimated potential saving in rupees. So others, what are you doing? There's no support for Michelle and Daham, Yasita, no support. Huh? There's only 3. So if there are more feedback, so then we can do this in fast. Otherwise, we have to wait till get the at least one feedback. Okay, let's move forward. So there are two hints in this case study. 25% leakage in compressed air systems, and the monthly energy consumption is 110,000 kilowatt hours per month for this compressed air. And first you have to calculate the monthly energy loss. So then you can multiply the monthly energy consumption by the loss 25%, and you can get the monthly energy loss. And then to get that annual energy saving, then you have to multiply it by 12 and annual cost. So if you calculate the energy cost here, you can take it as 50 rupees. And from this one, from compressed air leakage reduction, you can achieve 16.5 million per year. So electricity cost, here you can get this electricity cost in this one, electricity cost. Here we have given you the cost. So you can divide this cost by the kilowatt hour. So then you can get cost per kilowatt hours. The hum. Okay. Okay. So the electricity cost is 50. Okay. So then finally we can achieve 16.5 million with this compressed air leakage reduction system. And in chiller efficiency improvement, there's again 20% energy saving opportunity there. So you have to follow the same principles: monthly savings, annual savings, and then annual cost. So finally you can achieve 16.8 million per year. Okay. So by addressing this compressed air leakage and improving chiller efficiency, the facility can achieve approximately 33.3 million cost reduction per year. So this represents a significant opportunity for immediate energy performance improvement. Okay. So then the next one, prioritize action to reduce energy consumption and improve performance. So it is actually very clear. We discussed these things. There are some quick wins, no cost, no low cost programs there. So easily you can fix compressed air leakages and reduce this compressor pressure and improve shutdown practices and optimize operating. So those kind of activities, the quick saving activities, and then you can plan medium investment type projects chiller optimization or sometimes installation VFDs for that motors, because I think there's around 40% contribution in motors. So you can use VFDs for motors and improve the insulation. And the strategic improvement, you can plan energy monitoring system, demand control system, and definitely ISO 50001 implementation, because the energy management system uh, for these kind of organizations. Now we'll move to this operational efficiency improvement. Operational efficiency improvement. So this focus on optimizing how this system operate, because we have to get that idea to do these strategies and reduction projects. So this improvement often require minimal investment and can be implemented quickly. One of the fastest ways to reduce this energy cost. We actually discussed this part. So these operational inefficiencies occurs when equipment operate in a way that waste energy. So these are actually few examples. And in our previous case study, also we noticed that there can be a situation like equipment run during non-production hours and operating compressors as excessive pressure or maintaining issues or unnecessary heating or cooling levels. So these inefficiencies occur due to poor operational controls and lack of awareness. So this is actually, we call this as energy loss pyramid. So this is a conceptual framework used in industrial energy management to illustrate the different level of energy inefficiencies within a facility and their relative impact on overall energy consumption. So the pyramid structure shows that the largest energy consumption, or the losses typically occur at the system design and operational levels, while equipment inefficiencies usually represent a smaller portion of total losses. So addressing these inefficiencies from the bottom of the pyramid upward provide the greatest opportunity to energy cost reductions. And at the base are the system design inefficiencies, which account for 20 to 30% large portion of energy losses. And then these operational inefficiencies, 10 to 20%, maintenance, 5 to 15%, and this equipment inefficiencies, 3 to 8%. This system design inefficiencies occur when overall design of energy system is not optimized for the process requirement. Hello? Who is this? Manjula? Do you have any questions?
No, sir.
Manjula, sorry, Manjula. Okay. Okay, where we, okay, the system design. So this system design can be happen due to overall design failures. So for example, sometimes oversized motors and pumps and poor piping and duct system design in inefficient process layout. So sometimes very familiar example can be sometimes for a small room, there can be a large AC system there. So these kind of inefficiencies, system failures. So this poor system design can cause continuous energy waste throughout the facility lifetime. And then these operational inefficiencies. Operational inefficiencies arise from how this equipment and system are operated on daily basis. So even well-designed system can consume excessive energy if they are not operated properly. For example, we discussed this equipment running during this idle period and operating compressors at unnecessary high pressures incorrect temperature settings. In our office room, we put Celsius temperature into 18 to 19 Celsius. So incorrect temperature settings can consume more energy there. And poor scheduling of production equipment. So these operational inefficiencies significantly increase the energy consumption because this equipment continue to operate even when energy demand is low and unnecessary. So you can fix these kind of things by setting a standard operating procedures for energy management and improving production scheduling part, automated controls and timers applications, and definitely these energy awareness training sessions for your team or staff members. And the third one is maintenance issues. Maintenance is very most important one in this energy performance improvement because this poor maintenance increase friction, pressure losses, and heat transferring systems. And this maintenance related inefficiencies gradually increase this energy consumption and also may reduce the equipment lifespan. So definitely you have to focus about those maintenance scheduling part, and you have to implement regular inspection for those equipment maintenance part and the cleaning part. You have to establish cleaning procedures and checklist for those kind of equipment and proper lubrications. So those kind of maintenance activities you have to do, otherwise it will consume more energy. And these equipment inefficiencies occur when equipment operate below its optimal efficiency level due to outdated technology or poor design. For examples, we use some old low efficiency motors, inefficiency boilers, outdated compressors, old lighting system. Now, I think you all use LED lighting system. No one use these tungsten or CFL lighting systems. So although this equipment actually inefficiency contribute less than the other levels, upgrading equipment can still produce significant long-term savings. For example, if you are using CFL or tungsten bulbs in your home or the office environment, so by replacing that to the LED bulbs, so then definitely you can achieve significant energy saving long time. Okay. So addressing these layers systematically can significantly reduce energy consumption, but the greatest energy savings are usually achieved by addressing the system design and operational inefficiencies first. So now here actually we discuss main energy system in industries because we have to know about their characteristic and the energy performance strategies there. First one is motors and drivers. So electric motors represent the largest electricity consumption in industry. So we use motors in pumps, fans, compressors, conveyors. There are so many um, uh, functions we use these motors, and these motors we can plan improvement opportunities inside these systems by planning high efficiency motors, by setting variable frequency drivers. So these variable frequency drivers control motor speed based on their load requirement. Okay. So this means a small reduction in speed can result significant energy savings here. Okay. So this motor system optimization can reduce electricity consumption by 10 to 25%. The next one, air compressed systems. So we describe this as the most expensive utility in industrial facilities. So these inefficiencies can be happen due to air leaks, pressure drops, improper compressor controls. So by regular maintenance and system optimizing can significantly reduce these energy consumptions. So why it is important, this regular maintenance? If you are not regularly maintain this compressors, it can block these air filters. So these air compressors use these kind of filters to remove contaminants such as these dust, oil particles, moistures, and so this clean filter ensures the proper airflow into the compressor system. So what happen when filters are blocked? So then the air flow resistance increase, the compressor must work harder to draw air, and a pressure drop occurs across the filter. So this increase the load on the compressed motor. So that's why these preventive maintenance are very important. And then this steam system widely used in industrial heating applications. So these energy losses can be happen due to the steam leaks, fault steam traps, poor insulations, and implementing the proper steam system and maintenance can reduce energy losses by 10 to 20%. And the AC system are responsible for maintaining indoor temperatures and the air quality. So there are energy saving opportunities in these systems by installing efficient chillers, adjusting temperature set points, and improving building insulations. So by optimizing the AC load systems can reduce energy consumption by again 10 to 30%. So now let's move on to these low cost energy saving measures. So they are actually these low cost energy saving measures are often the fastest and most cost-effective method of improving energy performance. So these actions do not require expensive equipment replacement. Instead of focus on improving how existing system operate. So energy audit frequently reveal that many industries facilities waste energy due to these simple operational issues. So again, here we have selected 5 options here. Switch off idle equipment, optimizing operating schedules, reducing compressed pressure, fixing of compressed air leaks, and temperature optimization. Okay. So this one, switch off idle equipment. So this is actually the one of most common source of energy waste in industrial facilities. So in many factories, motors, conveyors, compressors are and lighting system continue running during break, shift changes, sometimes maintenance period. So even though the equipment is not producing any output, it is still consume electricity. So when multiple machines remain idle throughout the day, so this waste energy can be significant. Okay. So here we have another case study here. There's a 15 kilowatt motor running idle for 4 hours per day. So now you have to calculate the annual waste cost considering the electricity cost as 50 rupees per kilowatt hour and considering the operating days as 300. Team, can you do this? Can you do this? This is actually very simple one. Can you do this? So I feel you all sleeping, huh? Yes, it okay. Okay. I'll give you only 2 minutes. 2 minutes, huh? Calculate the annual waste cost. So it will not take 2 minutes anyway. Any answers? Annual waste cost? This is a very simple one. Okay, we have one answer, two. Okay. What is the Daham, I think you have to check your answer again. Anyway, we need this annual waste cost in rupees. You have to convert this into financial values. Okay, let's move forward. So to calculate this energy waste, you have to multiply the power or the energy consumption by the idle time and the operating days. So then there you can get 18,000 kilowatt hour waste per year. And then you have to multiply by the unit cost. So then you will get 900,000 rupees per year. Okay. So to address this kind of issues, the organization can implement several measures such as automatic shutdown controls, programmable timers, operator shutdown procedures, and idle load monitoring systems. So this solution ensures that this equipment operate only when required for production. Okay. So then this is actually the another common inefficiency occurs when utility system operate longer than necessary due to poor coordination between this production schedule and utilities. So you can see here the production shift start from 8 to 4, but utility run 6 to 6. So then there's energy unnecessary overoperation there, and due to this energy waste. So here also there's one example, but I will not go with your team. So here also that 30 kilowatt hour compressor operate 2 hours longer than the required day. So then again you have to follow the same formula. You have to multiply the consumption of the power by hours and the date, and then you can get the annual waste energy waste here. So these type of situations you can optimize by setting strategies like aligning utility operation with production schedules and installing automatic startup stop systems, sometimes using demand-based compressor controls, and implementing energy management system for scheduling. So you can use these kind of strategies there. So then the equipment operate only when energy demand is required. So actually we discussed this compressor system in our case study also. So these are widely used in manufacturing facility and often considered the most energy intensive utility in these industries. So the amount of electricity required to compress air depend heavily on the operating pressure of the compressor. So high pressure requires more energy because the compressor must work harder to compress the air to higher level. So again, there's one example. If a compressor operate 8 bar pressure and reducing that pressure into 7 bar can reduce the energy consumption by 7% approximately. So if the compressor consumes 100,000 kilowatt hours per year. So then you can save 7,000 kilowatt hours per year energy savings there by pressure optimization. And here actually you have to think one another thing because this pressure optimization must be performed carefully to ensure this production equipment continue to operate correctly. Otherwise, you will be in trouble. These compressed air leaks are one the largest source in energy loss in industrial plant. So these losses can be happen due to these pipe joint, hose connection, valves, quick connectors, fittings, and couplings. Because this compressed air system operate continuously, even a small leak can result in significant energy losses. Here again another case study for you. A tiny hole, 3 millimeter hole, a leak at 7 bar pressure waste approximately 1.7 kilowatt of compressed power. So then again, you have to, you can calculate the annual waste there. The next one is temperature optimization. So this temperature optimization of the control is one another most important factor. So in this, many industrial processes operate higher or lower temperature than required. So that again increase the energy demand there. So energy consumption increase significantly when system operate outside optimal temperature ranges. So you have to focus when setting temperatures for particular equipment or machine setups. You have to focus about this thing. So adjusting this building cooling set point to 20 to 24%, sorry, 22 to 24 Celsius can significantly reduce the energy consumption while still maintaining a comfortable working condition. So that's why I take that one example there. So if you are switch on your office AC into 18 or 19, it will consume more energy. So maintaining that set point into 22 to 24% can reduce significant energy consumption in your facility. Okay. So this proper temperature optimization require the accurate temperature controls, calibrated sensors. That is one another important one because otherwise we will know whether these meters show us the correct figures or not, and then the monitoring of indoor comfort conditions. So those kind of things you can do to adjust these temperature optimizations. So it's very clear this significant energy saving can often be achieved through simple operational improvement without major capital investment. We discussed these things. Without capital investment, we can do this thing. So this low cost energy saving should always be the first priority in this energy management programs because they provide quick energy savings and short payback periods. But although operational investment can reduce energy consumption, many large energy saving require capital investment. For examples, including these what do you call this high efficiency motors, installing high efficiency motors, or installing variable frequency drivers, or implementing waste heat recovery systems. So then definitely you need high capital investment. So before implementing such projects, the organization must evaluate whether this investment will generate financial benefits. So this financial evaluation method helps decision makers to compare this investment cost and this future savings. So here actually we select four financial evaluation methods here: payback period, net present value, internal rate of return, and life cycle cost analysis. So this payback period is the simplest financial evaluation method, and it tells us how long it will take for the investment to recover its initial cost through energy saving. You can see this equation here. Payback period is equal to investment cost divided by the annual saving, energy saving. So, and there's one example, investment 500,000, annual saving 200,000, and the payback period is 2.5 years. This method is simple, but it has some limitations because it does not consider future economic factors such as inflations, interest rate, or the time value of this money. So therefore, while payback period is useful for initial screening, more advanced methods should be used for large investments. Okay, so that's why we discuss these net present value and other methods in these sessions. This net present value method consider the fact that the money today is worth more than the money in the future. So these future energy savings are discounted to their present value using discount rate. Okay, so this here the equation is the sum of cash flow divided by 1 plus r square t and deduct initial investment. So this R is discount rate and T is time period. So this R discount rate. Discount rate is the interest rate used to convert future cash flow into their present values. Okay. So it reflects the idea that money available today is worth more than the same amount of money in the future, because today's money can invest and earn returns. So this we call this concept as time value concept, time value of money concept. Okay. So for example, if you have 1,000 rupees today, you can invest it and earn interest. But if you receive the same amount, 1,000 rupees 1 year later, it less value because you miss that opportunity to earn interest. Okay, now actually this is not there's no actually possibilities to earn interest using 1,000 anyway. But you can use that example. So therefore, when evaluating this energy project, we discount future energy saving to their present values. So that's what we are doing here. So this discount rate, now there's a question where we get this discount rate. So there are, and why we are using this discount rate? Because this energy efficiency project generate saving over many years. So future savings are not equal to today's money value. So that's why we have to do this evaluation and apply this discount rate here. And there are common methods. We can use discount rates here. Typically, most organizations used the interest rate the company pay to borrow money. For example, bank loan interest rate, sometimes between around 12% or 14-15%. And some use the minimum acceptable rate of return. That means that there can be a company policy. We need this level of return requirement, 10% return requirement. So that minimum return of the company expect from those investment. So it can be a company policy. And some organization use weighted average cost of capital method. So that is actually combine of cost of debt and the cost of equity, and used by large organizations. So typically we can use that cost of capital and minimal acceptable rate of return for our analysis. So if the net present value of the project is positive, okay, if the net present value of this project is positive or greater than 0, it means the project generate more financial benefit than the cost. So then we can approve that projects, those kind of projects. So this net present value consider one of the most reliable financial evaluation method for long-term energy efficiency investment. Now this internal rate return system. So this internal rate of return represent the profitability of an investment as a percentage. So it is the discount rate at which the net present value become zero. So organization often compare this internal rate of return system with their minimum acceptable rate of return. So if the internal rate of return is higher than the company's required return, then the project is considered financially attractive. Okay. So when calculating this one here, the investment is 500,000, annual saving 200,000, and calculated internal rate of return is 28 to 30%. And if the company required rate is 12%, so then we can consider this as financially beneficial project. And then the next one, life cycle cost analysis evaluation method. Here we have to consider the total life cycle or the total stages of the equipment. So instead of purchasing, we have to consider other stages also. For example, this energy operating cost, maintenance cost, replacement cost, disposal cost. So we have to consider the lifetime cost. Here you can see, although this high efficiency motor equipment has the higher initial cost, it may significantly reduce energy consumption over time because its operational energy cost is lower than the standard motor. So this life cycle analysis help organization to make better long-term investment decisions. Okay. Now again, you have one case study here. I will share this case study through WhatsApp. Okay. Okay, there's a manufacturing company. They plan to install a variable frequency drive on pump system to reduce electricity consumption and improve energy efficiency. The company wants to evaluate whether the investment is financially viable. So they have given this project data here. In initial investment, 500,000, electricity saving 8,000 kilowatt hours per year, electricity price 50 rupees per kilowatt hours, project lifetime 5 years, discount rate 10%, company required return 12%. So now you have 5 questions here. You have to calculate the annual financial saving from VFD installation. Then you have to calculate the payback period. And then you have to, using the discount rate of 10%, you have to calculate the net present value of the project over a 5-year period. And finally, is the IRR or the internal rate of return higher or lower than the company required return? You have to find that one also. And based on all this analysis, you have to take your final investment decision whether we move forward with this investment or not. Team, can you do this one? We have a limited time now, so I need your response very quickly. Can you do this one? Or else I will move forward with the answers. Can you do this? You want to do this one? No any feedbacks. So this is the first time I say it will take time. Okay, take your time. Take your time. So once you finish one by one, Michelle, I think you can put the answers into the WhatsApp group or the chat. Okay, I will give you 15 minutes. Let's try. කවුද මේ මදු බඩගිනීද? ජෑම් පාන් එකක් ඕනේ කියලා තියෙන්නේ. WhatsApp group එකේ. මේ මදු කනවා විතරයි හැබැයි අපිට මොකුත් feedbacks නැහැ අපේ chat එකේනේ. මදු I don't know whether girl or boy. There's no any feedback to our case studies, huh? Okay. Okay, we get feedbacks, annual saving 400,000 rupees, payback period 1.25. Okay, correct. Go ahead, go ahead. Okay, we get more correct feedbacks. So this is your answers are correct. Huh? Your answers are correct. It's 1 year and 3 months. So to initially you have to identify this annual financial saving, and then by using that you can get this payback period 1.25. So actually in industrial companies typically accept this project because this is actually less than 3 years. So if the payback period is less than 3 years, typically these kind of projects accepted by industrial people. So these are financially acceptable. Net present value. So මදුගෙන් feedback එකක් නෑ අපිට නේ. ජෑම් බනිෂ්ක් හම්බුණාද දන්නේ නැහැ. Team, we have limited time, so we'll move forward with these answers. Yeah. So here you can wait. I will share my. I think I have shared this financial evaluation Excel sheet with you. Right. I think you can see my screen, Excel one. Can you all? Can you see Excel sheet? Okay. Okay, so move forward. So here, initial investment. So these are given. So you have to take the annual savings here. So you can do this by multiply the electricity saving by the unit cost, and then you have to do this payback period using initial investment divided by the annual savings. So then you will get this 1.25 years. In this net present value, I think I have given this table with the case study, so you can try this one. So initially it's 500,000, and net present, you can take this net present value by multiplying these discount rate factors. So here it's 1 plus this given discount rate is 10%. So here you can see I have linked this with B8. In B8 means the discount rate here. And then you can do that one for first year, second year, third year, fourth year, and fifth year. And same time you will get these present values here. And then total present values you can get with this sum. And net present value means with the initial investment. So then it's around 1.1 million. And so it is actually greater than 0. So we can say this project is financially viable project. And then the internal rate of return. So we have to select where this net present value becomes 0. So we can adjust this discount rate here. Yeah, so we can adjust this discount rate here. So if it is 30, it will reduce these values, and 50 again, it reduce the value. So here, like this, you can check where this net present value become 0. So that is the internal rate of return value. Right. So these are the answers. So you get, we discussed this thing. Net present value is greater than 0. So this is financially viable project. And then internal rate of return, it's 66%, and it's greater than the company required return. So then we can say this is financially again viable project according to this level analysis. Okay. So now again, there's another one case study here. So this is relevant to this life cycle cost analysis. So there are 2 motors and there are details here. So I need your quick engagement for this one. Do the analysis and give me the best option. What is the best option for this one? So I will share that case study again with the WhatsApp group. So there's a manufacturing facility operating a 15 kilowatt motor for pumping system. The motor consumes electricity throughout the year. The maintenance team must decide whether to continue using the existing standard motor or replace it with a high efficiency motor. Although the high efficiency motor has higher purchase cost, it consumes less electricity. The company want to compare the total life cycle cost over 10-year period. So you have to do the assessment. So they have given this initial data with you. So I will give you 2-3 minutes to do this one. Shall I do? Okay, take few minutes and let's try. Just try. කවුද? කවනේ කට්ටිය නිදාගෙන ඉන්නේ පොඩ්ඩක් මේ ඇහැරලා ගන්න හොඳයි නේ. හෂී කුමාරතුංග. Hashi, can you do this case study? Hashi. Okay, we get feedbacks. Okay, Michelle, here you have to consider the total life cycle. So can you remember that circle, the purchase cost, operational cost, replacement cost, disposal cost. So there are different life cycles, life stages. So you have to focus about that one. Okay, okay. I think we get the correct answers also. So let's move forward with this. With this Nadisha. Nadisha, you're correct. Huh? Here, first you have to get this annual energy cost for both motors, and then for you have to consider it for the 10 years time, and then you will get the energy cost. I mean, this operating cost for 10 years, and to get to consider the life cycle analysis, you have to consider the initial purchase cost also. So then for the standard motor, it's around 25.2 million. High efficiency motor is 23.76 million. So the answer is 1.44 million saving from the high efficiency motor. And actually in this example, we only consider about this initial purchase cost and the operating cost. But when you are doing this for the industrial application, you have to consider about the whole life stages, life cycle stages. Here we only focus about the initial purchase cost and the operating cost only. Okay, so here actually we use these 4 methods, but other than these 4 methods, there are many other methods you can use. For example, profit indexity, discounted payback period, cost benefit ratios, return of investment, benefit cost ratios. So then you have one question: why do we use the 4 methods in this energy management system or in this session? Because these 4 methods prefer because it cover different aspects in financial decision making. So this is a payback period. If you are focusing about quick investment screening, so then you can use this payback period. So yeah, you are focused about the project feasibility, then you can use net present value method. If you are using the comparison between different project, so then you can use this internal rate of return method. And if you are focusing the long term equipment cost evaluation, then you can use this life cycle cost saving analysis method. So together they provide a balanced evaluation of energy efficiency improvement. So now this technology only cannot achieve optimal energy performance because human behavior play a critical role. Okay, so therefore these behavioral programs are important component of an effective energy management system. So in many industrial facilities, this energy waste occurs due to routine operational practices rather than equipment inefficiencies. For example, equipment running during idle or non-productive hours, or sometimes light or AC system operate in unoccupied areas. Compressed air leaks not reported by operators. They have to report if there's any leakage, steam or compressed air leakage. They have to report. Otherwise, they will know. Sometimes the engineering know the maintenance team will not know about these things, and so these incorrect operating parameters maintained for sometimes long period. So these issues can persist because employees may not be aware of the energy implication of their actions. So behavioral energy programs aim to create awareness, responsibility, accountability among these employees. And these behavioral initiatives should be integrated into daily operational practices. So when these procedures are incorporated into standard operating procedures, these behavioral improvement become the part of routine operation. Okay. And for behavioral programs to be effective, organization must monitor their impacts, and definitely they have to provide these training programs. And sometimes recognition program can be established to motivate these employees, like department energy saving awards or recognition for the employees who identify the energy saving opportunities. So you can you have to focus about that behavioral part also. Then we'll go to this last segment, linking energy management with this ESG and sustainability part. So energy efficiency improvement have a direct environmental benefit, primarily through the reduction of greenhouse gases. So in many countries, electricity generation still depend largely on fossil fuel, such as coal, natural gas, oil. So when industries consume electricity, they indirectly contribute to the carbon dioxide emission from these power plants. Therefore, reducing electricity consumption lead directly to lower greenhouse gas emission. So here, this is actually one example. To estimate this impact, we use a parameter called grid emission factors. So this grid emission factor represents the amount of carbon dioxide emitted per unit of electricity generated. And in many countries, this grid emission factor typically range between 0.5 to 0.7. I think in Sri Lanka also it's around 0.761 or around 7 kilograms of carbon dioxide per kilowatt hours. So according to this calculation, uh, by saving 100,000 kilowatt hours per annually, for organization can reduce 60 tons or 60,000 kilogram of carbon dioxide per year. So this is why energy efficiency often considered one of the most cost-effective climate mitigation strategies. So many organizations quantify this emission reduction when preparing corporate sustainability reports or carbon inventories. And then energy management initiatives contribute to all three pillars of the sustainability: environmental, social, and governance performance. So this environmental pillar mainly focus on reducing environmental impact and protecting natural resources. So energy efficiency contribute to this by reducing the greenhouse gas emission, reducing fossil fuel consumption, lowering air pollution, improving overall resource efficiencies. Because energy consumption is one of the largest contributor to industrial carbon dioxide emissions. And this energy management program are often a key strategy for organization aiming to achieve carbon reduction or net zero targets. Then the social pillar. This social pillar focus on how organizations impact employee, community, and society. So these energy performance, energy efficiency contribute to the social responsibility by promoting responsible resource use, reducing environmental impact and communities, and improving workplace awareness about sustainability. And this employee engagement program related to energy conservation also help to build a culture of sustainable within the organization. And then the governance part or the pillar, the governance pillar, this is focused on transparency, accountability, and the responsible management practices. So energy management support governance by enabling organization to monitor and report energy performance, disclose greenhouse gas emissions, and establish measurable sustainability targets. Uh, so many organizations now publish this ESG or sustainability report where they disclose their energy consumption and carbon emissions. So energy management systems such as ISO 50001 help organization to implement structured monitoring, measurement, and reporting process, which strengthen this governance and the strategies or the transparency. And this energy efficiency is not only about reducing operational cost, it play a crucial role in supporting corporate sustainability strategies, climate actions, goals, and ESG reporting requirements. So by improving energy performance, organization can achieve both financial benefit and environmental responsibility. Actually, we experience this with our case studies also, how we can get these financial benefits. Okay, so to summarize today's session, we explored several strategies that organization can use to improve energy performance and reduce operational costs. So we start by identifying significant energy users and understanding how energy consumption occurs within these industrial systems. And then we discuss operational improvement and low cost energy saving opportunities that can be implemented immediately. And also we examine these financial evaluation tools used to justify the energy efficiency investments. And finally, we discuss how this energy management contribute to the sustainability goals and ESG performance. So these approaches together help organization to achieve both economic and environmental benefit through effective energy management. Right. So thank you all for your participation and engagement throughout this session. And if you have further questions regarding this energy management, carbon accounting, or sustainability reporting, or energy audits, please feel free to contact our team. So we'll be happy to support your organization in implementing energy efficiency and sustainability initiatives. So now it's your time. If you have any questions, you can ask now.
I guess there's no questions. So coming to the end of today's Energy Excellence Masterclass, I would like to extend my sincere appreciation to Mr. Rasita, Mr. Hashan, and Mr. Pushpika for sharing their valuable expertise and practical insights. I would also like to thank all participants for your time, engagement, and active participation throughout today's sessions. I hope this workshop had provided you with practical knowledge and actionable strategies to enhance your organization's energy performance and drive sustainable cost efficiencies. We look forward to continuing to support you in your journey towards energy excellence and sustainability. So feel free to contact any of the numbers or the mail IDs on the screen. And then thank you once again for joining us and have a wonderful evening ahead.
Okay, thank you, team. Thank you, Shehan. Thank you, Prokul team.